Hello. Before we go to the workshop presentation on the precision ratio compass, I'd like to give you some preliminary information about operating this instrument. In his writings, R.N. Elliott mentioned a tool which he described as a time-saving device. New Classics Library spent several years looking for such a device, and we finally found this one, which is used by professional draftsmen and architects. It is solidly made and highly accurate and is known as a proportional divider. Dividing lengths is exactly what it does. The distance between the 2 points at the narrow end of the compass is an exact multiple of the distance between the 2 points at the wider end of the compass. That multiple is represented by the numbers along the left-hand scale of the compass. By adjusting this slide, we can change the relationship between the two ends of the compass. Another way to view this is to consider the distance between the 2 points at the narrow end of the compass as the number 1, and consider that as either the numerator or denominator of a fraction. The number at which the compass is set on the left-hand scale, then, is the other side of that fraction and represents the wide end of the compass. The fraction itself is the ratio which relates the narrow and wide ends of the compass. For example, if we set the left-hand scale at the number 3, then the distance represented by the narrow end of the compass is 1 over 3, or 1/3 of the distance represented by the wide end of the compass. Conversely, the distance represented by the wide end of the compass is 3 times that represented by the narrow end of the compass. If you look at the lower portion of the right-hand scale of the compass, you will see a special line placed there for your convenience, marked with the letters GS, which stands for golden section. Setting the compass on this line produces the ratio 1 to 1.618 between the narrow and wide ends of the compass. By setting the compass at GS, you are able to calculate quickly all of the reliable Fibonacci relationships you'll ever need, without a calculator and without ever having to reset your compass. Here's how to do it. You will notice a small notch on the back of one leg of the compass and a small tab on the front inside of the other leg. Line these up and then close the legs of the compass so that the 2 points at both ends are perfectly aligned. Now, loosen the wheel about 1/2 to 3/4 of a turn, which will allow you to adjust the slide. Notice the hash mark across the lower portion of the slide. By moving the slide, line this hash mark up with the corresponding hash mark on the right-hand scale next to GS. Then tighten the wheel. That's it. Your compass is now set at the Fibonacci ratio, so that the narrow end of the compass and the wide end of the compass, regardless of the various lengths which they may happen to measure, are always related by 1 to 1.618. One last note. These things are sharp, so please be careful. Now let's go to the workshop. What we're going to look at today is how the proportional divider, how the PRC, can be used to save you time when you're looking at different Fibonacci calculations. Now this chart is on page 273, and what this is the same chart as is on page 272 without the numbers. The chart on page 272 is just an idealized wave structure which is full of Fibonacci relationships for the purposes of illustrations in this section. There are many, many other real-time examples in your workbook. We'll look at some of them in a little while. That's what this chart was done up for. This is the same chart that appears in the PRC manual. Everything that we discussed today is in the PRC manual. When you're using the precision ratio compass for measuring price objectives, what you want to measure is the length of this move. You do not measure this way, because if you measure across this axis, what you're measuring is price as well as time. You're incorporating both of them into what you're measuring. All you're interested in measuring in this case is the price action. So if you wanted to measure the length of this move from this point to this point, because you wanted to take Fibonacci relationships with regard to that, you would place the compass at the origin of the move, and you would place it at a vertical equivalent
to the terminus of the move. If I want to measure the length of this move, I place one point of the compass at the origin, and I place the other, what we refer to as a vertical equivalent, to the terminus of the move. For those of you who are interested in looking at Fibonacci time relationships, you would use the compass in the same fashion, except you would measure along the horizontal axis. If I wanted to see, well, gee, is there any relationship between this piece of the chart and this piece of the chart, you would measure along here. Page 273A shows some Fibonacci ratio relationships. And these, I've always been fascinated with these. I won't go into them in detail other than to say that they're very interesting, and you have them in your workbook so that you can look at them and enjoy them later on. The number 618, or phi, times itself as 382. Bob mentioned that. But if you continue multiplying times phi, this is the series that you get: 382, 236, 146, 0.090, and so on. Additionally, though, if you start with 1 and subtract 618, and then subtract the next number in this series, you'll see that 618 minus 382 gives you 0.236. 382 minus 236 gives you 146. 0.236 minus 0.146 is 0.090, and so on. We'll take a look at the lower portion of this chart in just a moment. Well, that's all well and good, so what? Now, with the compass set on GS on the right-hand scale, let me show you its value. I've got this 5-wave structure, and I'm interested in getting Fibonacci retracements of that because I want to see where a potentially corrective wave would end. So we set the old stopwatch. Oop. I measure the move. Let's see, I won't talk my way through this time. Okay. Oh, 26 seconds. Okay, that is a new world's record. It's official. It is official. I wanted to come in under 37, and that was good. What did I just do? Well, hopefully, what I've done now is measure every Fibonacci retracement that I would ever want to use relative to a 5-wave structure, or relative to pretty much any price pattern. 0.618, 0.382, 0.236, and 0.146 in under half a minute. Without a calculator, I have no idea what prices this move started at or where it ended. But what did I do? Let's take a look at it. You measure the length of the move when you're looking for a retracement, when you're looking for a number less than 1, you start with the wider end of the compass, which is what we did here. You measure the entire length of the move. Now, what do we know about the narrow end of the compass at this point? It is 618. It is 0.618. The distance between the 2 points at the upper end of the compass is 0.618, the distance between the 2 points at the lower end of the compass. Therefore, all I need to do is flip the compass, measure from the top. What I'm doing is subtracting 0.618 from the peak of that. Therefore, this point marks a 62% retracement of that entire structure. What I did next was measure up from the bottom of the move without adjusting anything at all on the compass, leaving it fixed with the narrow end. And in doing so, I'm subtracting the difference between 1 and 0.618 is 0.382. Therefore, that mark is a 38% retracement of the entire move. 1, 2, 3, 4, 5. Now, the upper chart is more important right now. What did we just look at? Additionally, 0.618 minus 0.382 is 0.236, and 236 minus 146 is 0.090. So what I can do at this point is contract the compass, and it doesn't matter which end I use right now, and I took the difference between 0.618 and 0.382. I came up to the top, and I subtracted it from the peak, and now I've got a 0.236 retracement. I contracted it again. I took the difference between 0.382 and 0.236, and that gives me a 0.146 distance. Sorry, 0.146 distance, and I subtract that from the peak and make a mark, and that's a 0.146 retracement of that entire move. Now, there is an alternate way to do that, and I'll show you very briefly. I had the compass initially set measuring the entire distance CD, and I flipped it because I know that the narrow end is 0.618 of the wide end. And I measured 618 and I measured 382. I could also have contracted the compass again because I know that 618, which is that length that I've just marked, times 618, which is now the distance between the two narrow points of the compass, gives me 0.382, as you can see in the chart at the top of page 2.73a. And therefore, that would give me the same measurement doing it in that fashion. Additionally, since I know that 382 times 0.618, which is how I have my compass set, will give me 0.236. I can measure 382 with the wide end of the compass. 618 of 382 is 236 on the narrow end of the compass, and so on. I contract it one more time. With the wide end of the compass, I measure 0.236 times 0.618, subtracted from the peak, gives me 0.146. So whichever way you're more comfortable using the compass to make these measurements is fine. The way I did it first is the way I'm more comfortable. And I can promise you that if you use it for a day or two and you just measure a few charts, you'll be an expert with it. You may not know what to do with the numbers right away, but you'll be an expert at using the compass. Let's take a look at page 275. Excuse me, first let's go back and take a look at 273a. At the bottom of the page, remember, with the compass set at GS, the distance between the 2 points at the bottom is 1.618 between the distance between the 2 points at the top. These relationships that are shown on page 273a apply as far as 1.618 is concerned. And you see a similar relationship as what we saw with 0.618, in that the multiplicative relationships and the additive relationships yield the same numbers. And again, there is no other series of numbers with which this works. 1.618 squared is 2618. 2618 times 1.618 is 4.236, and so on. 1 plus, we start with unity, 1 plus 1.618 is 2.618. 2.618 plus 1.618 is 4.236, and so on. Let me mention now, although you could take this down or up to very, very small or very, very large numbers, we rarely see moves or relationships which have forecasting value that are smaller than 0.236 or larger than 4.236. And we'll take a look at a couple of examples of those. Now let's take a look at page 275. Suppose you've got this structure here and you're interested in getting Fibonacci multiples. And usually when I say multiple, I'm talking about a number that is larger than 1. You're interested in obtaining Fibonacci multiples of this length here, the A wave. For example, to estimate the peak of wave B or the low of wave C. But the distance that you're interested in is distance AB. If you're interested in a multiple, if you're interested in a number that is larger than 1, you want to begin with the narrow end of the compass. Just the opposite of what you would do if you're looking for retracements. And you measure that length, AB. Then, flipping the compass, the length between the 2 points at the bottom of the compass is 1.618 times AB. So if I were to come down and just make a mark right there, for example, that length is 1.618. This length is 1. I measured that, flip the compass. That length is now 1.618. This length is now 2.618. You can obtain it in that fashion. 1 plus 1.618 yields 2.618. Or I could just measure 1.618 with the narrow end of the compass, flip the compass again, and make a mark. And this length would be 2.618. Then the sum of 1.618 and 2.618 is 4.236. Because 2.618 times 1.618 is also 4.236, I can measure with the narrow end of the compass, 2.618, flip it, and the wider end would then also be equal to 4.236. Essentially, in less than a minute, you can have every retracement or multiple that you would ever be interested in using when you're counting waves and looking for other estimates as far as the ends or as far as support or resistance areas are concerned. Let's take a look at page 276. Let's suppose you've counted 3 waves up. And you're expecting wave 4. If wave 4 were to fall to a 38% retracement of wave 3, where would it come? Well, you don't know what price this is. You don't know what price this is, although let me mention on the original page the prices are there and you can bang them out on a calculator and see that these numbers are exact. With the compass, however, I'm looking for a 38% retracement of wave 3. I measure by putting the compass at the origin of wave 3 and a vertical equivalent to the end of wave 3. Then, because 1 minus 0.618, which is now the narrow end of the compass, equals 0.382, I just come up, I make a mark right there. I think we'll see. You've got your retracement. You have no idea what price this is, what prices exist here. Let's take a look at page 277. Wave 2s are always difficult to forecast. Let's suppose you were looking at what would be a 62% retracement of wave 1. in this structure. You're looking for a retracement, so you begin with the wide end of the compass. You measure the length of your move, flip the compass, which now equals 62% of that length, subtract it from the peak of wave 1. Make a little mark, and you've got your measurement. I guess I should mention, I think all of us around the office would use the compass to quickly see if there are any targets which would cluster, fall into the same area, and then you can go to your calculator if you want to bang out exact numbers because you're putting in an order and you don't want to be off by 10 ticks, or for example, as far as an estimate is concerned. But these are, the precision ratio compass will give you an exact mark on the chart. If you can read the level on the chart, then there would be no reason for you to have to use a calculator to double check that. Let's take a look at page 278. Wave 3 was equal to 1618 times the length of wave 1. This example, within wave 3, this chart is labeled in this fashion, do that for the sake of reference. Let's suppose you think you're getting an extended wave here within this third wave for various other technical reasons. Well, what if within intermediate wave 3, minor wave 3 is going to be 1618 times the length of wave 1? You're looking for a multiple. So you begin with the narrow end of the compass and you measure wave 1 of 3. If you flip the compass, since it's set on GS, the distance between those 2 points is 1618 times the distance that you just measured, which was wave 1. And if you add that to the low at wave 2, it gives you a projection for wave 3 equal to 1.618 times wave 1, as is shown in the example. Page 279. If wave 3 can be 1.618, the next, and you think that for some reason it might be longer, or you're just interested in taking that measurement, the next most likely place to look would be 2.618 times the length of wave 1. So here's the structure that you've got. And let's say you're thinking that you might be getting some type of an extension here. Since you're looking for a multiple, you begin with the narrow end of the compass. And you measure the move you are interested in obtaining a multiple of. Flip the compass, and now the distance between the wide end, the points at the wide end of the compass, is 1.618 times the distance between the points at the narrow end. 1 plus 1.618, if I make that mark right there, is 2.618. And then I can just take the compass, expand it, and add that, should be exact, and add that to the low at intermediate wave 2 to obtain a projection for where intermediate wave 3 would be 2.618 times the length of intermediate wave 1. As an alternate, you could also do this in this fashion. You're looking for a multiple, you're desiring 2618. You measure 1 first with the narrow end of the compass. You flip the compass and make a mark. That's 1618. Now, since 1618 times itself also equals 2.618, you could flip the compass again using the narrow end, measure 1.618, that you just measured, and then the distance between the 2 points at the wider end of the compass is 2.618 times that original distance. So you can do this in either way. It's whichever way you become more comfortable with it. Let's take a look at page 280. These are some real-time examples. When primary wave 1 completed in January of 1984, Bob said, for various reasons, what would occur, or where would a 38% retracement be? Because that would be a logical place to look for support for the end of primary wave 2. What would we do in that case? Well, we're looking for a retracement. We start with the wide end of the compass. We measure the length of primary wave 1, which is that length as shown on the chart. And remember, since we're looking for a retracement, we start with the wider end. Flip the compass. And measuring up from the low, in this case, if you make a mark, you've just separated that line into the Fibonacci ratio, 618,382. And that point, the hash mark, shows a 38% retracement of primary wave 1 as an estimate for wave 2. Here's what took place. This is page 281. Let's take a look at page 282. We talked about wave 3s equaling 1.618 times the length of wave 1. Here's that same example. Primary wave 1 and 2 have been completed. If I'm looking for wave 3, primary wave 3 to equal 1.618 times wave 1, what would I do? I'm looking for a multiple. So first, I start with the narrow end of the compass and measure the length of primary wave 1. I then flip the compass, and all I need to do is add that distance, add that length to the bottom of primary wave 2 to achieve a target, an estimated target, for the peak of primary wave 3. Page 283 shows how that worked out. Now, we've heard that there are certain relationships that apply in 5-wave structures. And one of the relationships is in regard to extensions. When wave 1 is extended, a good place to look for the end of wave 5 is that point where the net travel of waves 3 through 5 is related by 618 to the length of wave 1. Well, let's see what took place here. First of all, we're looking for a retracement, in the sense we're looking for a number smaller than 1. So we start with the wide end of the compass, and we measure the length of the move, which we've labeled here on the chart as an extended wave 1. Flip the compass, subtract that distance from the peak at wave 2 to obtain a target for the point at which the net travel of waves 3 through 5 would equal 0.618 times wave 1. Now, when this occurred, we looked at this chart a couple of times yesterday. This was that diagonal triangle that completed in July of 1986 and was a very pretty pattern. There were a couple things that took place at this time. First of all, there was this thing called the Prechter cell signal that people blame the decline on, and well, we don't know if we believe in those or not, actually. But there's something that, to stay safe, I'll say I don't know if I believe in this or not either. Program trading. People said at the time that if it weren't for program trading, the market would never have fallen to this level. All right, but Fibonacci knew otherwise, and when you think about it, it makes sense, because who programs the computers that do the program trading anyhow? That's people, And I guess that psychology applies. But in spite of both of those obstacles, program trading and sell signals by gurus, what did the market do? The best labeling for this structure in real time, and it has not been altered, was that the market came down in a 5-wave structure, finished minute wave 3, rallied in a wave 4, and came down and double bottomed at that point in wave 5. And the net travel of waves 3 through 5 was exactly 62% of the net travel of wave 1. Let's take a look at page 286. In corrective patterns, there are typical relationships, particularly in a zigzag, that you expect the waves to follow. In the first place, you would look for a C relative to an A wave would be a 62% multiple of that. So you look at C equals 0.618 times A. And the next place you would expect to look would be C equals A. And after that, C is 1.618 times A, and so on. So let's see what happens here. Suppose you're looking at this structure, and you're interested first in the length of A. Now you're looking for C equals 618 of A, so you begin with the wide end of the compass. Flip it, subtract that distance from the B wave, and obtain a target for C equals 618 of A. Now you didn't know that was going to occur, so you would have made that mark, but you probably also would have said, well, let me take a look at C equals A, because that's pretty typical, and that occurs quite frequently. So there's the length of A, and you subtract that from B, and you make a mark. All right, at that point. Now, why is that target less likely? Because it's down in the volume on your chart. Okay. So in this case, let me just say, in this case, C equals 618 times A was correct. Although, in practical purposes, you would look at both. Let's take a look at wave 1. That's the length of wave 1 in this, what we think is a new impulse wave to the upside. 62% of wave 1. I measure with the wide end first, flip the compass, I've got 62%. And I make a mark. And we see that that was a good estimate for the low of wave 2. Additionally, if you've got internal calculations within wave 2, in other words, the first place we would look is, okay, let's see wave 2 equals 62% of wave 1 as a target. But within wave 2, we can also look at relationships between waves A and C to see if we get a confirming target, if we get a cluster of Fibonacci calculations. So in this case, let's take a look at the relationship that works, because you'd plot all of them. You plot C equals 618 of A, which probably doesn't even get you to a new low, so you'd throw that out. You plot C equals A, which is somewhere up here, probably in the previous 4th wave, so you'd pay attention to that one. But then you plot C is 1.618 times A, times the length of the A wave, and in order to do that, you measure with the narrow end of the compass first. You flip the compass, subtract that distance from the peak at the B wave, and you make your mark. And I think those lines are actually a little bit closer than I've got them drawn, but what you see is that at the same point at which wave 2 retraces 62% of wave 1, Within wave 2, wave C is 1.618 times A. You've got a cluster. That's the point at which you want to pay more attention to the action if prices get down there. Now, we also discussed yesterday, and this is a very good example, the idea of counting failures. Now take a look at this relationship, at this pattern right here. You've got an A wave down, you've got an ABC up for B. If you count down as follows, you can go 1, 2, 3, 4, 5 to this point and count that as a C wave, potentially. But is that the right thing to do? And the answer is no, because it's a failure. And remember we said that failures and corrections were very rare, and it's a low probability outcome, and you shouldn't do it. And what you should bet on instead was that that 5-wave structure would subdivide into a 9-wave structure, ultimately, and that was a higher probability outcome. That's exactly what took place in this pattern. All weekend long, we've talked about how Elliott has a fixed set of rules. There is a very important set of rules that go along with the precision ratio compass, and there are 2 of them. The very first rule is that the precision ratio compass can only be used on arithmetic scale paper, and the reason for that is that it measures lengths. It does not measure the proportions between percentages, so you cannot use it on semi-logarithmic paper. Now, fortunately, most of the charts that are available are on arithmetic paper, so that does not pose a problem. The second rule with the compass is that you should never, ever drop the precision ratio compass in your lap. That ends the section on the precision ratio compass. Thank you very much. We're going to take a break of, I would guess, about 10 minutes. 10 minutes? Okay. Thank you. And Bob will be up to do his options section next, and that's one that you don't want to miss.